Welcome back to Physics with Miyoshi. We're going to talk about a little bit more about momentum, and today we're going to talk about the conservation of linear momentum. The definition, as it says up here, is that in a closed system, linear momentum is conserved when the vector sum of the average external forces acting on the system is zero. Well, first of all, you got to ask yourself, what is a system? Well, the nice thing about a system is you define it. The thing is, you have to define it in such a way that the momentum is conserved oftentimes. So if I have two balls here, and this shows before and after, if you will. So if I drew the line here, this is before and this is after a collision. Before the collision, maybe they're traveling toward each other, and then they collide here, and then they come off in different velocities. Well, if I define my system in such a way that it includes both of these guys, then momentum should be conserved in that case. If I define it as just one of these objects, then it won't be conserved in that case. But if we define it correctly, then we should be able to see that momentum is conserved. And how we do that is we go back to the impulse momentum formula, if you will, and we look at the forces. And normally what you do is you define the external forces and the internal forces. And so if we look at the first and the second mass, if you think about them, the external forces acting on it plus the internal forces acting on it times our time, which is just our impulse, then that's going to equal our momentum, our change in momentum, our mass 1 times velocity final minus our mass 1 times the velocity initial, which is over here as well, the mass and the final mass and the velocity. The same thing would be true in mass 2, external forces plus our internal forces times our time. It's going to give us our impulse, and that's going to be, again, our change in momentum. Now, why do we look at the external forces versus internal forces? Well, the reason why is because if we look at it properly, our internal forces are anything acting on each other. So at the time of collision over here, when they're actually touching each other and colliding and, pushing on each other, if you will, then the internal forces are those forces that, if our system is defined as the two objects, then those two forces acting on each other have to be equal and opposite based on Newton's second law. So according to Newton's second law, then these two guys have to go to zero. Okay? And then we still have, our change of momentum. We can add these two equations together so that we look at both of them as a system, and we can see that our external forces and our internal forces, these guys are equal and opposite according to Newton's second law, and then we'll multiply that by time. Is still our these guys here are mass 1 times velocity 1 final minus velocity initial, and the same thing for the second mass. And then we rearrange the equation, and we're going to get we'll take that guy out, and we'll just talk about the external forces, and then we can rearrange these guys so that this initial ones, or the final ones, are together and the initial ones are together. So this is our total final momentum and our total initial momentum. And then if we figure out, if we isolate this system well enough, if we define our system over here well enough, then our total external forces should be zero as well. When we do that, then we can see that this guy over here becomes zero. And then if we rearrange this, this guy equals zero. Then we can rearrange that. Zero equals this guy over here, the final total momentum and the final initial momentum. We can rearrange that to show that the initial momentum must be equal to the final momentum. Now, I only showed two objects here, but this would be true no matter how many objects you have. As long as we define our system properly, we can say that our momentum should be conserved. And that is the law of conservation of linear momentum. There would be one as well for rotational momentum, but we aren't going to talk about that right now. That's why we talk about linear right now. But notice that you can think about this if you've ever played pool or billiards. Then you can think about how you hit one ball and hit another one. You can think about Another classic example is a system of trains where you have two cars colliding with each other, and then they get coupled together. This is the same kind of thing here as well. So we'll talk about that more as we talk more about momentum and in later episodes of Physics with Miyoshi. So thanks for tuning in, and we'll see you next time for more Physics with Miyoshi.